Once again, welcome everyone. Thank you for joining us for this IT Learning Hub webinar, NatMech's presentation on validating and leveraging probe data to understand travel patterns and identify candidate operations projects. This webinar is being presented as part of the series partnership with the National Travel Monitoring Exposition and Conference, or NatMech. Understanding highway travel demand patterns are critical for transportation network analysis and planning. Traditionally, transportation professionals relied on questionnaire-based surveys to gather information on travel patterns. Through such stated preference surveys provide important information on general travel patterns, they inherently lack the ability to capture dynamic components of real-world travel behavior. Additionally, significant effort and resources required for these surveys often restrict the frequency or spatial coverage of their deployment. Probe vehicle-based data service providers leverage devices equipped with GPS to provide time-stamped. Excuse me just a moment. Okay, there's just a slight audio thing there. Probe vehicle-based data service providers leverage devices equipped with GPS to provide time-stamped location information of travelers for broader coverage over time and space. This allows agencies to build trip details like origins and destinations, departure times, route and mode choices, and travel times, allowing opportunities to fundamentally change how we study travel patterns. Today's learning objectives are to understand what vehicle-based probe data are and how it is collected, to recognize how probe data may be used through different case studies that analyze travel patterns or identify project sites to improve operations and mobility, and become familiar with distributed acoustic sensing solutions that convert spare capacity within roadside fiber optic cables into a distributed sensor cable of continuously monitoring traffic flow along the monitored route. I'd like to introduce our presenters for today's webinar. We have Rick Ayers, the Public Sector Advocate for the University of Maryland CATT Laboratory. We have RJ Porter, the Highway Safety Engineer for VHB, and Paul Cooper, the Business Development Director for Transport Market OptiSense. And today's Q&A moderator will be Sarah Worth O'Brien, the Senior Research Associate at UNC Highway Safety Research Center. And at this time, I would like to introduce our first presenter. And our first presenter today is Rick Ayers. Rick, whenever you're ready, you can go ahead.
Fabulous. Thank you, Kellyanne. And real quick audio check. Do you hear me okay?
Yep, hear you loud and clear. All set.
Fabulous. Just wanted to say thank you to NatMech as well as session organizers for having the CAT Lab participate in today's session. Again, my name is Rick Ayers. I'm the Public Sector Advocate for the CAT Lab, the Center for Advanced Transportation Technology Lab. Today's agenda, I want to cover several things, largely some really interesting, innovative, and cool technology that the CAT Lab has developed for a number of our users across the country to help uncover and explore trip travel patterns across the United States. I want to start with a quick overview of some of the data sources that we leverage to support this web-based solution as a service. And then I'm going to walk you through the 3 tools that are within this trip analytics solution or software as a service. Origin and Destination Matrix tool, a segment link analysis tool, and I'll wrap up with a quick overview of our route analysis tool. Most of you, or some of you that are on the line today, may be familiar with the Center for Advanced Transportation Technology Lab out of the University of Maryland, but for those of you who are not, we kind of characterize ourselves as the industry leader of applied big data analytics for transportation applications. Most of our users across the country leverage our platform. This platform, software platform is called RITIS, Regional Integrated Transportation Information System. Most of our users support various operational activities, planning activities, and some research for their respective organizations. We do take pride in the fact that we develop, manage, and operate the world's largest transportation data archive and analytics platform. That exists because we've been doing this work for nearly 15 years, recording and archiving every minute of every day for every road segment across the United States probe data. So significant number of resources and assets at our disposal to perform some very, very interesting big data transportation analytics. So these are the three tools within this broader web-based solution as a service that I'm going to cover today. Again, OD Matrix, segment link analysis tool, as well as route analysis tool. Before I jump into an overview and exploration of these tools, I did want to cover, I wanted to cover some of the data sources and the data that's used by this web-based solution. While Trip Analytics as a software solution is architected to support any number of trip or travel-based data sources, we have architected and delivered out of the box with Trip Analytics some incredible data from our friends at INRIX. So we've partnered up with INRIX. They have a super comprehensive, rich collection of various different types of data sources that contribute to about 100 million plus trips per day across the United States. These different data types are coming from sources like long-haul trucks, service delivery vehicles like box trucks, and the systems that they use for delivery, as well as consumer-based sources, so in-car nav systems, the GPS feeds that are coming from those vehicles, as well as mobile phones and those devices where you've enabled location-based services. So this collection of sources, again, contributing to 100 million plus trips per day, INRIX collects some unique identifiers, location, heading, and speed information. They take these pings and they try to extrapolate discrete trips from all of this source data. So INRIX has this really comprehensive business logic on the back end. As you see in this slide here on the left, they have a number of, they got all these pings from a source of a trip. These blue pings are the path of the trip, and here you see the destination where somebody ended up at a shopping mall, it looks like. So they take all of those pings, those individual data points that are being collected from those various different types of sources, they align that with a road network, snap it, and then that becomes a trip path. So they're doing this every day with their back-end business logic to develop that 100 plus million trips per day. So while that's the source for the out-of-the-box capabilities of Trip Analytics, just wanted to give you some context there. This is the landing page for this web-based, cloud-based solution as a service we call Trip Analytics. As you see here, we have a number of states that have already kind of gotten on board and leveraging this INRIX data, these tools that I'm going to share with you. Each state may have 1 or more years worth of data, so they have some temporal comparison work that they can do as well. The first tool I'd like to explore with you is the OD Matrix tool. The OD Matrix tool, as the name implies, is really a way to leverage that rich trip data from INRIX to create some fairly basic OD matrices from a number of different filters. All of the tools within Trip Analytics are fed through a series of filters or input queries that are spatially defined, temporally defined, and also filtered by trip type. You see what I mean here in terms of spatially defined types of origin and destinations for this OD matrix analysis. Here for Rhode Island, we see that there are counties as options, sub-counties, maybe you've got jurisdictional boundaries, as well as transportation analysis zones. These are the levels of geography that come out of the box with trip analytics and are available through all of the tools. Once you've defined the origin and destination geographies that you're interested in analyzing for the OD matrix, you can establish the temporal parameters. So we have some really nice visualizations to define the time of day that you're interested in, the days of the week that you might want to query against or analyze, as well as months of the year and multiple years. And then consequently, you have, because INRIX is providing us and this user community for trip analytics 3 different types of data sources or trip data sources, you can filter out your trips by vehicle type: light vehicle, medium vehicle, heavy vehicle, any combination of the 3. Once you've established all those input parameters, the OD matrix tool generates this matrix. For Rhode Island, it's not too complicated, right? There's only a few counties. We can see that there's just a few counties for the results here. Notice in the upper right-hand corner of the OD matrix tool, there's a link here to generate a chord diagram. So once you've looked at the OD matrix, you've explored that a little bit. You want to take a look at some other data visualizations for that data. For the OD matrix tool, you have this dynamic chord diagram that lets you explore each of the counties or geographies that you selected and see what the origin and destination trip counts were for each of the origin and or destination geographies. There's also a nice little top 10 OD pairs. For this analysis, we see that Providence to Providence was the primary OD sets of trips. I'm going to step in now to the segment analysis tool. Segment or link analysis, as it's commonly referred, gives users the ability to select a roadway or a series of roads or some corridor and explore or uncover the trips that move through that corridor in a specific direction. Here we're analyzing westbound traffic along this segment, this green segment of roadway along the Belt Parkway. And we're going to ask this particular tool, the segment or link analysis tool, based on the definition of the road or the length that we want to analyze, the level of geography that we want to analyze. Again, we have out of the box counties, sub-counties, and transportation analysis zones. And what we want to look at from an OD perspective, origin and destination geographies, or some combination of those. Again, I didn't put any example screen grabs of the trip filters or temporal filters. Once that's been established, you run the query, this is the result. So again, this is the link or the segment or the roadway corridor that we wanted to analyze. And this mapping visualization shows us in orange all of the origin county-based geographies that trips began from, and all of the destination geographies or counties in blue that trips ended up in. Each of the polygons or counties, this mapping interface is very interactive. So as with any other mapping interface, you can zoom in and out and explore the various, investigate and explore the various geographies, determine what the county was, what the trip count was for each of those to get a better sense of what those trip patterns were from those origin and destination geographies. Within the link analysis or segment analysis tool, you can toggle, once you've explored the map visualization, you can explore a matrix. So here we see that this OD matrix has been generated from the analysis. You could take a look at specific values, things that kind of pop out from a destination perspective. And then note, all of the tools within Trip Analytics have a form of interoperability that's available for them. At the top of this particular, at the top of the matrix tool, you've got an export button, allows you to take the matrix, the results of the analysis that you just performed, and then you can integrate that into your own BI tool, or maybe you want to dump this into your own organization's GIS platform of choice. Lots and lots of flexibility for you to take the results of your analysis and explore it further. On that note, one of the distinctive features about all of the tools or trip analytics as a whole is that we give our users the ability to download the raw data. Unlike a lot of other consumer-based trip analytics tools that lock up the data and make it proprietary in a sense, trip analytics allows you to kind of explore the raw data for your own needs. The segment analysis tool, we're finding a lot of our users are really finding it useful to study temporal patterns from year over year or month over month. In this particular scenario, there's a small segment of roadway here that's been identified outside of Baltimore, Maryland, and the user, state of Maryland, they wanted to determine, hey, are there any anomalies that occurred from an origin and destination perspective between 2018 and 2019? And in this case, there's, it was largely very similar numbers from an origin and destination perspective. Here's an example in Rhode Island where Rhode Island DOT, they studied a segment of US 1 inside of Massachusetts to kind of get a sense for, again, any anomalies that may have developed between July of 2020 and August of 2020. You see the origins, destinations, the trip counts labeled in those respective jurisdictions, and again, not a huge difference. So some really nice tools to quickly go back in time, reanalyze, and compare the difference if you have that data. Moving on, just going to wrap up with an overview of the route analysis tool. Route analysis tool is one of my favorites within Trip Analytics, and that there's some cool functions and features that I'll share with you in a little bit. But again, here, as the name of the tool implies, this gives you the ability to identify a series of origin geographies, sort of interactively through a drop-down list of either counties, sub-counties, or transportation analysis zones again. Destination geographies, any combination of the two. Again, set your temporal parameters as well as whether you want light vehicles, medium weight, or heavyweight vehicles as part of your analysis. In this scenario, or in this screen grab that I took, you see our origin geographies that have been selected by the user here in orange, and these are the destination geographies, sub-county geographies for the analysis. When the user hits submit, the tool, and then of course you got to define your temporal parameters and the types of vehicles. Once you hit submit, this is the results page. You get a mapping visualization that illustrates all the routes that were taken between the origin and destination geographies, and a list of all the routes and the number of trips within each of those routes, sorted by the greatest number of trips to the least number of trips. I want to bring your attention to something really interesting and that our users really like. It's not totally apparent here, but there's 1,117 total trips that were returned from the analysis. Those aren't all represented in this list of 12 routes. This is a scrolling list. So every single trip, if it was one trip and one route, or 306 trips along a certain route, we've pulled that data out of that trips database from INRIX. So really, really rich insights to kind of extract or explore with this route analysis tool. If you weren't interested in looking at all of that data, you just wanted to maybe look at, hey, I'm only interested in 10 or more trips, the routes that were taken for 10 or more trips. Maybe you have some time-based considerations, duration, greater than or less than some duration. There's some additional filters within the route analysis tool to support that. If you were to turn on, in this example or in this scenario, as you see here, if you turn on all of the routes in the top 10 list with the number of trips comprised within all of those routes. This is the mess that in the map that you get. But as with all the other mapping visualizations within Trip Analytics, you can explore that further, zoom in and zoom out on your origin geographies or destination geographies, take a closer look at, oh wow, these are the routes that were taken into these destination geographies. Well, that's kind of cool, Rick, but how do I pull out some of the details to how many trips came in from this route or these other routes? Well, we have this really cool ScreenLine tool that allows users to digitize on screen basically an arc, a segment that intersects all of those roads or all of those routes, and it breaks down the percent and numbers of trips that pass through each of those routes. You do the same up here in the origin geographies. Notice that based on scale, you may get a couple of overlapping routes within a certain map extent. And then when you're ready, you want to see the details, you just click the ScreenLine summary, and it gives you a breakdown of the number of trips for each of those intersections of the ScreenLine along the routes that you'd analyze. In addition, you've got this ability to copy and paste the coordinates of that ScreenLine so that if you wanted to go back and perform some analysis on a different time period, you can do that again by copying and pasting those coordinates. This is a feature that was widely requested by our users. We rolled this out just a few weeks ago, and this gives you the ability to say, hey, you know what, I don't want to select my destination geographies, but I do want to understand all the routes that were taken from a origin geography. So in this scenario, we've selected an origin geography in the northwest corner of the state of Massachusetts, and we've said, tell me, based on the temporal parameters and vehicle type, tell me all the routes that were traveled out of that jurisdiction or that geography. And interestingly, you can zoom in on that and perform the same ScreenLine analysis that I illustrated just a moment ago to get some detailed breakdown of the number of trips and the percent breakdown. We're also providing the capability to upload into Trip Analytics unique custom geographies. So we have a few states that have said, hey, we want to share with you a shapefile or a GeoJSON file. We can support that as well. You upload your custom geographies and you can perform this same analysis. So that's all I have to share with you today. Thank you again to conference and session organizers. This is my contact info. And Kellyanne, I pass the baton back to you.
Thank you, Rick. And at this time, we will now move on to our second presentation by RJ Porter. RJ, whenever you're ready, you can go ahead and get started.
All right. Good afternoon, everybody. Thank you all for being here for this webinar. I'm happy to represent my co-authors in presenting this work that we had submitted for consideration by the program coordinators of the National Travel Monitoring Exposition and Conference. So again, great to be here for this webinar. This slide just gives a brief overview of what I plan to cover today. The primary focus of my presentation will be on an effort that we undertook to try to find promising spot mobility projects in North Carolina. That served as the basis for our conference abstract, but I do want to provide also some quick insights to some work we have continued that built on the rural spot mobility experience. And so first, focusing on that first effort on the rural spot mobility projects, I'll provide a little bit of background and the objective of the work, a little bit about the data and methods, results, and future directions. And you'll see that I'll primarily stay focused on that application level and what we were trying to do and what we were trying to learn from the analysis. A little bit of background of this project was the North Carolina Department of Transportation, or NCDOT, Spot Mobility Program, which seeks to systematically and objectively invest spot mobility funds to projects or programs that reduce congestion and delay times across the state. The program has an annual cap, and projects also have a cap. Individual spot mobility projects were capped at a maximum investment of $750,000 per project. And so projects could focus on improving operations at the corridor level or at specific intersections, ramps, driveways. Mobility countermeasures would obviously vary by location, but they can include new traffic signal installation, traffic signal revisions, adding or revising left turn lanes or right turn lanes, and so forth. At the time of this particular effort, which we undertook in 2017, NCDOT had noted that it could be challenging to find promising spot mobility candidate sites in areas that are not covered by metropolitan planning organizations. So NCDOT had primarily relied on regional traffic engineer input and other NCDOT staff input, but there could be other candidate sites that are out there that maybe are not generating complaints or possibly are unknown to the NCDOT staff. And so the purpose was that the DOT sought a method to systematically scan and find and prioritize such sites, again, especially in rural and small town areas. And the idea being that such an objective and systematic performance-based approach would get the spot mobility program off to a good start and demonstrate a good return on investment. One thing that we kept in mind as we developed the method was that the NCDOT Spot Safety Program provided a really good model of the type of method that we were looking for the Spot Mobility Program, with the focus of this effort being on sort of that network screening step, where you're screening network-wide, identifying a significant number of sites with potential for further investigation. Trying to synthesize that into the objectives of this particular study, they were to develop a method to systematically scan NCDOT roadways outside of areas covered by MPOs to look for promising spot mobility sites, and then to execute the new method and develop a ranked list of sites with potential that NCDOT could utilize to develop candidate mobility projects. So as you'll see, and I'm sure you've experienced, the ultimate goal and the types of performance measures for this type of operational network screening step are pretty straightforward and fundamental. The approach and the data itself, particularly the integration and analysis of probe data across the entire state road network that is as large as North Carolina's, that was our key step forward in this first effort that I'll talk about. So just a little bit of highlights of the types of data sources that we looked into with the support from the DOT. We gathered a variety of data sets for potential use in the operational analysis and screening. We gathered these from a variety of locations, including NCDOT's online data layers, RIDIS, which we just heard about in the previous presentation, and some data that were directly provided by the NCDOT Spatial Analysis Group. So this included things like the linear referencing system base file with roadway inventory information for the state road system, speed limit, shoulder widths, median widths, and so forth. Daily traffic volumes from the DOT's traffic survey, GIS data products and documents. Again, here data was key to our effort, downloaded directly from the RIDIS using the massive data downloader. The analysis ultimately in this work used here data from the second Tuesday, Wednesday, and Thursday from each calendar month in 2017 during the AM peak and PM peak periods. TMC segments that were conflated to NCDOT's network, and this was provided by NCDOT at the time of this effort. And then, of course, county boundaries, MPO, RPO boundaries, division boundaries, and urban boundaries, that will that we used to, as we summarized our results, say by region, by county. We had also initially gathered crash and rail crossing bike routes data to have as part of this framework. We ultimately didn't use it in the analysis, but as you'll see, tried to set up a sort of a flexible framework here that future efforts could continue to test different ranking methods and determine their impacts on the results. After data collection, we reviewed our analysis data set from a quality control perspective. At the time, we had a focus on the quality of the conflated TMC segments. NCDOT was also undertaking a quality control related to this, and it was still ongoing at the time of this effort. And then after we collected and processed the data, we brought everything into a single geo database with the same projection and coordinate system. So as you'll see, we were ultimately interested in a mobility analysis that was score-based to identify these sites with potential for mobility projects. We utilized a series of different types of parameters and calculations to assist in the scoring of these segments that might show potential for mobility improvements. We developed a series of parameters using ArcGIS spatial and tabular analysis capabilities. And again, we wanted NCDOT to have the ability to update and change the operational analysis and the scoring to test the impacts on the results and to vet the results. And so bringing everything together through this type of spatial integration offered us this type of flexibility. Obviously, there are many different ways that such an analysis could define analysis time periods when looking at volumes and capacities such as daily, hourly, sub-hourly. Similarly, one could look at a variety of ways to score and rank segments based on operational performance, segment characteristics, and apply different weights to those different factors and time periods. We were taking a first step here, and in taking this first step, we decided to keep the planning level analysis focused on daily volumes and daily capacities and travel time indices, as you'll see. But again, we built in flexibility into the method and the tool that we ultimately developed so that we could and NCDOT could test a variety of what-if type scenarios and make adjustments relatively easily over time as experience with the approach was gained. This just shows how we assigned a capacity to each segment in the data set using daily capacity from NCDOT's their spot prioritization process. So just showing in the table in this slide, the capacity assignment was necessary, as you'll see, to support the operational analysis and the scoring activities that I'll discuss. And so as you can see here, this is a planning level assignment. It's applied at the segment level and is a function of facility type. So now getting into the method and the scoring, after a number of meetings we had with NCDOT staff and some sensitivity testing, this first release of this spot mobility analysis and scoring was based on two parameters, as I mentioned, the daily volume to capacity ratio and the travel time index. The daily volume to capacity ratio was estimated by dividing the average annual daily traffic volume by the daily capacity. As previously noted, we assigned that daily capacity to each segment using the numbers from NCDOT's spot prioritization process. And so the top table in this slide provides the volume to capacity score that we assigned to each segment based on estimated daily volume to capacity ratio. And then our travel time index was estimated as the ratio of the segment travel time while traveling at the average speed for a given time period to the travel time at the free flow speed, with free flow speed set to the posted speed limit. We had downloaded here data in 5-minute intervals during the AM peak period, again of the second Tuesday, Wednesday, and Thursday of each calendar month, and averaged the average speed values across those time intervals to obtain the average speed during the AM peak. Similarly, we had downloaded data in 5-minute intervals during the same PM peak periods of the second Tuesday, Wednesday, and Thursday, and again averaged the speed values across those time intervals to obtain an average speed during the PM peak. The AM and PM peak average speeds were then assigned to the road segments on the base map that I previously discussed. And again, the conflation of the TMC segments to link the HERE data to NCDOT's network. NCDOT was able to provide that to us as part of this effort. So the HERE data were directional. So the average speeds were available by direction, and so we had to develop some different ways to integrate depending on if the LRS was also directional. So for a divided facility, if it was directional, then we applied directly the directional average speeds from HERE. If the baseline in the LRS was bidirectional, such as for an undivided facility, then we took the directional speeds in HERE, we averaged them prior to assignment. And again, there's some different approaches that we could potentially take here that I'll talk about towards the conclusion of this presentation. Again, we then estimated actual and free flow travel speeds for each segment using the posted speed limit, and then we computed the travel time index for both the AM peak, the PM peak periods, and then averaged those for scoring. And so that bottom table then brings that all together on how the average TT or travel time index score was assigned to each segment based on that average of the AM peak and the PM peak travel time index. So we then added the scores for the daily volume to capacity ratios, the average TTI scores for an overall operational score. So as you can see here from the table, scores range from -2, which would be your poor performing operating segments, and to 1.25, which would be your top operating segments. Again, segments outside of areas covered by MPOs with negative overall scores were ultimately identified for further investigation by the regions. Again, I mentioned the decision to base scoring for this effort on daily volume to capacity ratio and travel time index. But again, we built in the ability to score and weight other parameters if that type of testing is of interest. These parameters could serve as surrogates, for example, of potential operational issues. One example could be the lack of a median, or narrow median could indicate a high likelihood of no left turn lanes, and further weight a location for a potential spot mobility project. Similarly, a narrow shoulder could indicate minimal room for clearing an incident, and further weight a location for a potential spot mobility project. And so just some example placeholders that we built into the tool are shown here on the slide for illustration purposes. We ended up building a dashboard tool to share the results of the operational analysis and scoring. The figure in the slide here is a screenshot of the dashboard with the primarily rural counties layer turned on. And so overall, the dashboard has multiple layers that allow users to view different categories of results. We have an NC routes all roads layer, which shows all roads from all counties with an operational score. We have a layer that has the results for primarily urban counties. This shows the screening results from the 10 most urban counties with an operational score. Again, the primarily rural counties are shown here. These show the results for all but those 10 most urban counties with an operational score. And again, these results were the primary focus of this study. A couple other example layers, we built in layers showing planned projects. And so again, users could, if a segment showed up as a site with potential, you could test it against what was already being programmed for that location. So things like at the time, the 2018 intersections that were identified as part of the Highway Safety Improvement Program, the 2018 HSIP segments, and we had a layer with the 2018 through 2027 STIP, which shows the spatial location of projects on that STIP. And so the users of the dashboard can also filter the results by the NCDOT region as well. Clicking on any segment with an operational score then pulls up a window and it shows data for that segment. So the route ID, route number, number of through lanes, route name, and then the basis for the scoring, including that estimated daily volume to capacity ratio, the travel time index, and the AM and the PM, and how that all comes together into that operational score. In the end, as we work with NCDOT and sort of the size of that list that they wanted for further investigation, we, again, those segments with a negative score became the focus, and the results showed 609 road segments with negative operational scores to identify for further investigation. And these were spread across the different NCDOT divisions and regions. Ultimately, the data and analysis seemed to prove effective at providing an approach, an objective, systematic and performance-based approach to scan the network and identify candidate sites for further investigation for potential spot mobility improvements. The Transportation Mobility and Safety Headquarters and regional staff had a meeting, this was back in August 2018, where the regional traffic engineers met. We went over the approach and tool, and they had concluded that it would be useful for identifying candidate sites. In a follow-up verification effort, members of NCDOT looked at a sample of 16 funded spot mobility sites and found that the tool would have identified 11 of them when looking at the operational scores. As with other network screening approaches, there's conditions and circumstances that can influence the results, things like speed limit transitions, cross-section and through lane transitions, longer-term work zones, accuracy of the segment data, and particularly the posted speed limit data, is very important for this type of operational score, and in some cases various seasonal influences as well. So this slide summarizes some potential improvements to the next version of the rural spot mobility tool, including, again, testing the sensitivity of results and the accuracy of results with different approaches to scoring, including considering some of the segment geometric characteristics, possibly the safety performance. Others related to, maybe a different way to aggregate that data at the segment level, for example, using the lowest directional average speed as opposed to the average of the directional speeds when assigning the HERE data and coming up with the travel time measures. Possibly looking at single peak periods in the AM or the PM alone versus, as we did, we sort of brought AM and PM together and looked at some average conditions, and possibly looking at segments that maybe don't have HERE data as part of the overall scoring. Maybe there'd be some sort of parameter to weight road segments with ADTs above 5,000 vehicles per day. This would give road segments without HERE data, but with ADT greater than, say, 5,000, some type of operational score. We also think the availability of having a more detailed intersection inventory would certainly assist in how sites are defined and analyzed compared to the planning level facility type segment approach that we took. Future evolutions of the tool and scoring could also explore approaches for estimating hourly volumes as a function of daily volumes and other roadway and contextual characteristics. So certainly a lot of future opportunities here. And just with the remaining few minutes, I just want to show a couple more highlights that end up building on our experience using probe data for the Rural Spot Mobility Project. The first, based on the experience that we had gained as part of that effort in utilizing probe data to analyze the state network, we had an opportunity to continue some of the work as part of looking for ways to advance data-driven scoring that is part of NCDOT's approach to developing its statewide transportation improvement program, which identifies projects that will receive funding over a 10-year period. NCDOT's process funds projects in 3 categories: statewide mobility, regional impact, and division needs. The statewide mobility category focuses on significant congestion and bottlenecks, and selection of projects is 100% based on data-driven approaches. There's a regional category to improve connectivity within regions. Selection is based on data and local input. And similarly, there's a division focus, a division category of projects that address local needs, and selection is based 50% on data and 50% on local input. The key point here is that all three types of funding categories score congestion, and congestion receives its largest weight in the statewide mobility category, to focus on significant congestion and bottlenecks. And so given the experience gained on the prior rural spot mobility project and seeing how data might be used at that network planning level, NCDOT was interested in exploring how you might evolve away from, say, an estimated V over C from a travel demand model to congestion and travel time reliability measures based on actual observations over time periods, leveraging their access to the probe data. And so again, results to date have been promising. This is just one example based on 2018 HERE data from RITIS at 1-minute time intervals over PM peak periods, looking at the percent of time a segment is congested, defined by speeds less than 75% of free flow speed. So we're looking at the analysis for a number of different time periods and thresholds, really still considered in that exploratory stage of the effort on how this information might be integrated into the statewide scoring. I know I'm running out of time here, so just to sort of wrap up, one advancement as part of this was that we made since that rural spot mobility effort is in finding ways to identify the source of congestion on different segments to better define the needs and potential projects. So this is a good example shown here where looking at segments alone, one might say that TMCs 2 and 3 are the issue. They're in congestion for the longest period of time, but when you're able to bring in that spatial and temporal characteristics of the segments, you can start to uncover what actually is the source of the congestion starting at that earlier time period on TMC4. Just one final effort that I'll mention, and then I'll conclude because I know I'm running up against my 20-plus minutes here, but we had some other efforts where we're starting to look at the integration of probe data and speed estimates from that data into safety analysis. And this was one particular effort focused on pedestrian safety. Just in short, safety studies often rely on surrogates for measures of speed, things like posted speed limit. And so we've been looking at ways to, again, integrate actual estimates of speed into safety models. In this particular case, we were looking at predicting the severity of a pedestrian crash that has occurred and the probability that the pedestrian crash will occur. And we were able to integrate probe data with data from the Highway Safety Information System, City of Charlotte, NCDOT, and Mecklenburg County, and I think show some very interesting insights that we hadn't been able to previously gain with safety modeling that, again, had to heavily rely more on surrogates for speed. And so with that, I'll conclude here. Again, ran a little bit over, but happy to answer any questions at the conclusion, and feel free to reach out by email as well.
Thank you, RJ. We will now move on to our final presentation today by Paul Cooper. Paul, whenever you're ready, you may go ahead and begin.
Hey, thank you, and hello to everybody on the call. So first of all, just to say I am, again, also very pleased to have this opportunity to present to you all today about our experiences in applying fiber optic sensing technologies to enable existing roadside fiber optic cable to be converted into a traffic monitoring sensor for various clients that we have worked with in Europe and North America. So first of all, just a short introduction to our company OptaSense. As some of you on the call may not be familiar with us. We're a British company. But we're a wholly owned subsidiary of Luna Innovations, who are a NASDAQ-listed company based in Roanoke, Virginia. But OptaSense as a business is 100% focused on the design, the development, and the delivery of fiber optic sensing solutions. And this is technology which enables us to convert standard single-mode fiber optic cable into becoming an intelligent distributed sensor, which is capable of monitoring long asset distances with a minimum of deployed hardware or deployed equipment. So just to put that into context, for each deployment of the OptaSense hardware, we have the ability to monitor up to 50 miles of distributed asset. So of course this gives this technology a fundamental advantage over point sensor alternatives, simply in terms of the amount of hardware which needs to be deployed to site. Given that advantage, not surprisingly, you will see from the slide that OptaSense operates in a number of market verticals, all of which are characterized as being dominated by long linear assets. And in each of these industries, we deliver essentially the same technology, but we deliver domain-specific sensing solutions and applications which enable our customers to better protect and also optimize the performance of their assets. So before talking more about fiber optic sensing technology, let me make a quick assessment of the market for traffic sensors as I see it. So most of the road operators and owners that we talk to and work with have already made significant investments in their intelligent transportation systems, and many, if not all, will have deployed multiple roadside sensors costing, upwards of tens of thousands of dollars per mile in terms of their investment. But even at these budget levels, they have often had to limit sensor coverage or deployment density due to the CapEx and the high OpEx costs which are associated with common point sensor technologies, such as inductive loops, video detection, or microwave detection systems. Additionally, probe data sources. Obviously, we've heard in the previous two presentations that these provide an awful lot of value. And whilst they are maintenance free and do provide that value, they do have their own limitations in terms of latency, sample rate, and perhaps limited functionality for some traffic management applications. So whilst during this presentation, I will of course highlight some of the performance and operational advantages of fiber optic sensing solutions over these alternatives, I will emphasize at the start that it is my opinion that all traffic management technologies have their unique advantages and drawbacks, and that fiber optic sensing technologies should really be viewed as being complementary to existing investments and these alternative sensor technologies. Okay, let's now discuss more about fiber optic sensing and how the OptaSense TMS, the OptaSense Traffic Monitoring System, can convert spare capacity in fiber optic cables into becoming a traffic sensor. This infographic, which you can see now, pretty much gives a high-level overview and the story on one slide. So what I'll do is I'll talk around the panels in this, and then we go into a little bit more detail on the following slides before discussing a few case study experiences. So looking at panel one, our technology, it converts roadside fiber optic cable into becoming a traffic sensor. Specifically, we're looking to utilize the spare capacity in the form of a single dark or unused fiber core and convert that into an intelligent traffic sensor. On to panel two. What we do is we connect up to that dark fiber the OptaSense equipment. Now the OptaSense equipment comes in a 19-inch rack-mounted format, and typically this is installed well away from the roadside, typically in an equipment room or a network hub building where the required power, the environmental controls, and access to the fiber is available. And as said previously, from each deployment site, we're able to monitor up to 50 miles of asset, 25 miles in either direction, and for longer asset distances, we can network these systems together. On to panel three. What the technology does is it converts the actual fiber core into becoming the intelligent sensor. I'll explain how this works in a little bit more detail on the next slide, but put simply, laser technology enables us to convert the dark fiber into an array of several thousand distributed virtual sensors. onto panel 4. Each one of those sensors is able to detect the traffic as it passes along the monitored road. And it does that by each of the virtual sensors reacting to a combination of the noise and vibration associated with the vehicles traveling down the road. So we're able to detect the traffic, and the processing algorithms that we've developed enable us to convert that detection into a number of highly accurate and timely traffic flow indicators down the monitored road section. So the primary output of the OptaSense traffic monitoring solution is an average speed, an aggregated speed across the lanes of the highway, but an average speed which is delivered with a spatial resolution of about 150 feet every 50 meters and updated once every second. And because we're able to monitor the average speed to that fine degree of resolution, we're also able to monitor closely for changes in the average speed. So we're able to quickly and rapidly identify areas of congestion, slowing traffic, and also areas of queuing traffic where the traffic has stopped. And we're able to identify those areas, both the head of the event and the dynamically growing tail of the queue, again to within an accuracy of 150 feet, 50 meters. We're also able to use the average speed to provide journey time estimates between configured locations, which are most typically junctions. And in addition to the 4 traffic flow indicators which you see on the slide, all of those are achieved with a fiber optic cable running parallel to the road. In the cases where the fiber optic cable is running underneath the road or perpendicular to the direction of traffic, in those cases we're also able to count the traffic and provide flow rate calculations. So let me now explain some of the principles of the technology and how we use a technique called distributed fiber optic sensing to indeed convert that roadside fiber optic cable into becoming a distributed traffic sensor. So this is a road application. We have a section of road. As said, we require a fiber optic cable which is running parallel to the road, and we require access to one of the dark or one of the unused fibers. And we connect up to that fiber the OptaSense equipment, and the proprietary item of hardware which we supply is called the interrogator unit. And one of the major components of the interrogator unit is a high integrity laser. So the interrogator unit will send a series of laser light pulses down the fiber optic core. And for each and every laser light pulse that is sent, a proportion of that light will be reflected or backscattered back to the interrogator unit. Actually picks up on impurities in the glass fiber. So the interrogator unit is able to not only send the laser light signal, but it's also able to look for and understand the properties of the reflected light signal at 150 foot intervals down the fiber optic core. And the trick is that when something actually happens on the road, and in this case we're looking to detect vehicles traveling down the road, a combination of the noise and the vibration associated with the vehicles traveling on the road causes a microscopic disturbance to the fiber optic cable, the fiber optic core. And that will change the properties of the reflected light signal. So the interrogator unit is able to detect that change, and the processing algorithms which we've developed on top of the interrogator unit enable us to convert that detection into the traffic flow indicators which you see appearing on the slide. And as said previously, the top 4 of those are all achieved with the fiber running parallel to the road, and at the points where the fiber optic cable is perpendicular or running underneath the road, at those points we're able to count the traffic and provide flow rate calculations. So having explained how the technology works, I think it's worth just giving you an insight into the kind of data which we're able to collect or generate with this system, and then how we display that data as traffic information to our customers. So the bottom window here is not normally exposed to our customers in operations, but what it does show is it shows the raw acoustic data which we have collected. So on the x-axis, you've got distance, and on the y-axis, you've got time. And each of the black lines that you see running diagonally on that chart, each one of those will represent a vehicle traveling along the road. It is essentially the acoustic noise and vibration generated by each vehicle traveling down the road. The direction of the signal, going from left to right or right to left, gives an indication into which direction the vehicle is traveling, whether it's going on the eastbound lanes of traffic or whether it's going on the westbound lanes of traffic, for example. And the gradient of the line gives an indication as to the speed of the vehicle. Additionally, the intensity of the line or the blackness of the line, that gives an indication as to the type of vehicle. So we do get an insight at that point as to whether we are looking at trucks or whether we're looking at lighter vehicles. On the top part of this chart, you get a first look at the OptaSense graphical user interface, which is the way that we present the traffic information to our customers. So what you're looking at here is you're looking at two directions on a highway, an eastbound and a westbound, and the color-coded band is an indication of the average speed. So the green is showing areas where the average speed is good or normal, and as the color goes through the spectrum to orange and red, in those areas that's where we're starting to see queuing and congestion. And in those areas we are able to send alarms and notifications to our customers to alert them of that incident. You can also see the journey time calculations, the travel time shown on the diagram. Okay, so with that kind of explanation, let me just now talk through a selection of projects which have been delivered recently using this technology, both in Europe and North America, and at least for us in the UK, as far away as we can get in New Zealand. So I think the first thing to note on this slide is the type of roads which we typically monitor using this technology, and which I believe are really the sweet spot for this kind of technology. So typically we're looking at multi-lane, major strategic highways and arterials. And obviously, if there is already fiber optic cable running parallel to the road, then that obviously helps with the investment case for the solution. I think the other thing to point out on this slide is in in the majority of these cases, with the exception of North Dakota, we were able to monitor these roads using existing fiber optic cable. So in the case of New Zealand and the Netherlands and also Atlanta, Georgia for the Georgia DOT, the fiber optic cable was a standard telecoms fiber optic cable located in the shoulder of one of the lanes of traffic. And in the case of Georgia DOT, we were able to monitor 5 lanes of traffic in one direction through the central area, and then 5 lanes of traffic in the opposite direction. So I hope that gives some insight into the sensitivity and the sensing range of the technology. And also in Sweden, the fiber optic cable was running down the center of the road. So obviously we could monitor either side of the fiber optic cable and differentiate between those different directions of traffic. So just pulling up onto this slide the OptaSense graphical user interface for each of these projects. I'm not able to animate these for you today, unfortunately, but 2 things to point out. First of all, this is the OptaSense graphical user interface. Most of our customers look to integrate the underlying data into their own traffic management user interfaces, and that's easily achieved using a standard API. And I hope if you look at the Swedish case here, I hope you appreciate that on these extended road sections of probably upwards of 20 miles there, you can see the granularity to which we're able to provide this average speed measurement at 150 feet intervals and update that once every second, which I think is a resolution which is not practical to achieve with other technologies. So just moving on to the next slide, whilst fiber optic sensing is still an emerging technology in the traffic industry, and we're still working with our early adopters in North America, I'd just like to give some confidence to the accuracy of the solution. And many of our early adopter customers have gone through independent validation of the accuracy of the solution compared to either ground truth or the sensor sources which they currently trust. And for this North American audience, just to point out that the Swedish Trafikverket and the Dutch or the Netherlands Rijkswaterstaat are both generally recognized in Europe as being leading innovators. So they've really put a lot of effort into the validation of the system. In the case of Trafikverket, we've done a lot of comparison and validation against microwave detection devices. And just on this snapshot, I hope you can see that there's a lot of correlation between microwave and the OptaSense solution. With Rijkswaterstaat, they did pretty much the same, an independent consultant, but in this case it was in inductive loops. And you can see that even if we zoom in on that, there is still a high degree of correlation between the accuracy of the OptaSense solution and the inductive loop technology. In the UK, we did extended activities on an instrumented tunnel testbed, which is populated by a high density of CCTV cameras. And in this project, each and every time that OptaSense indicated a queue or congestion event, that was compared to the CCTV cameras. And you can see from the reports that we scored 100% in terms of detection accuracy, and also the detection time was much more rapid than with alternative sensing technology. And then finally, just in the case of Georgia DOT, obviously we did the same kind of validation against their existing sensor sources, but another thing we were able to do was during a monitoring period, continually monitor their Twitter feed for incidents, and then each and every time we saw something on the monitored road section, we were able to relate that back to what we were seeing on our system, again to give good confidence. Okay, so I think I'm okay for time, but getting close to summing up now. So just really to talk now about the two main areas I think where the OptaSense solution has some advantage, and the reasons why customers in Europe and elsewhere are investing in the technology. So the first of all, I think, is this ability to gain very granular, high-resolution speed information over extended road sections with a minimum of deployed hardware, speed every 165 feet, updated every second, and the very accurate queue and congestion detection. And also the ability to leverage existing investments in fiber optic technology. And I think the other main area of benefit is the operational benefits. So a lot of these stem from the fact that we significantly reduce the amount of equipment that needs to be deployed roadside. Each system is covering up to 50 miles. And the equipment that we deploy is very robust in service. It's completely unaffected by weather, road maintenance, wear or renewals, and has an ultra-low maintenance burden. So the life cycle costs of this solution are extremely favorable when compared to alternative point sensor solutions. And the other point to add is that the installation is pretty rapid and simple. We can have a 50-mile road section being monitored within about 2 weeks. and there's no requirement for any road or lane closures. So that, again, is another operational benefit. So finally, the summary slide from me. I think I've spoken enough to the performance and the operational benefit advantages. But again, I think I will finish this presentation by again emphasizing that, you know, we see the fiber optic sensing solution as being complementary to existing ITS investments, complementary to probe data sources, but equally we see it as an additional source of high quality traffic information, which may in turn give road owners and operators the opportunity to both optimize their operations and also potentially retire or reduce their reliance on existing sensors and data sources, which may be costing them a lot from an operational perspective. Thank you very much, and I'll hand back.
Thank you, Paul. We will now move on to the Q&A portion of this webinar. So at this time, I will hand it over to Sarah to begin the Q&A.
Thanks, Kellyanne, and thank you to all of our presenters for very interesting and thoughtful presentations. If you think of an additional question, please feel free to go ahead and add it into the question pod whenever you get a chance. But we'll go ahead and move through, and I'll jump around a little bit between presenters. So first up is a question for Rick, which is, what is the basis for determining the trip type or the purpose of a trip that you might be looking at?
Yeah, Kent, that's a great question. The source of the data for our out-of-the-box solution, Trip Analytics, is derived from INRIX. And one of the slides that I shared with you indicated that there are a number of different sources of their 100+ million trips per day that they consume through a variety of different partners of their own. Of those trips and data sources that they collect, they know, INRIX knows, whether or not it comes from a passenger vehicle, whether or not it comes from a sort of a medium weight vehicle like a box truck, and or a freight truck. So it's that at the source that INRIX knows and can consequently label, identify, and tag each of the trips with its different vehicle type. And then we're able to just leverage that in terms of filtering and identifying those different vehicle types. In terms of the purpose of the trip, there's no insight or transparency to that whatsoever.
Okay, thank you. Now to RJ, a question of how was the daily capacity estimated? Was the peak hour capacity divided by the peak hour factor?
Those daily capacity values, they're actually part of NCDOT's planning model and planning process, and I think there's some reports available out there on how NCDOT goes about their estimation, but they look at things like speeds and facility type, the number of lanes, the signal density, and other factors related to that particular type of facility. And so on that table I showed, again, you sort of saw it separated by facility type, a median presence, and the number of lanes. And then kind of behind the scenes there, you got some typical speeds for those facility types. And then you can, use a factor to just go from, say, an hourly capacity to an estimate of a daily capacity. And so we just wanted to, for this effort, maintain some consistency there with those numbers that they use for as part of their planning model.
Thank you, RJ. Now over to Paul. Someone had a question of, can the fiber line for the traffic counts also be simultaneously used for other non-traffic functions?
Okay, thank you very much for the question. So the system that I described today, that actually uses a dark fiber within a, typically within a multi-core fiber optic cable. So whilst the fiber optic core, the dark fiber optic core which we use is dedicated to traffic monitoring, the remaining cores in the fiber optic cable can be used for non-traffic functions. And that's true for the perpendicular fiber used for the traffic counts, and also the parallel fiber used for the other traffic flow functions. Technically, it is possible to employ this technology onto a lit fiber, a fiber which is already being used for non-traffic functions. But generally, we at OptiSense choose not to do that, and many of our customers ask us not to do that because they like to have a clear separation between the traffic functions and the non-traffic functions. And often that is because the the owner of those different cores within the fiber optic cable may be different. I hope that answered your question.
Thank you, Paul. Now back to Rick. This is actually a question that I had. How can you tell whether there might be a changed trip? So, in other words, you've got all these origins and destinations. Say a vehicle starts at one origin, goes to a store, goes to a daycare, goes to a business center. How do you know what is a discrete origin and destination? Are all of those counted as discrete OD pairs, or is there the possibility for missing any kind of individual trips or trip chains?
Yeah, that's a very good question, and insights that I don't have at the tip of my tongue. We would have to go back to the source provider, INRIX, and the business logic that they use to perform the snapping of all of those unique trip pings to a roadway segment and to generate an individual trip. There are some details to that business logic that I'm not privy to, but I could certainly follow up with the group to get some of that. Great question, though.
Yeah, I was thinking about it with the route analysis tool specifically, and showing that there's lots of different ways to get from point A to point B. And it made me think, well, maybe you see some of those seemingly out of the way routes because people are they're chaining their trips.
Correct. And that is taken into consideration when INRIX generates a trip for a number of pings for a unique ID. I mean, they know that, that a single device is originating its trip at a particular location, and within a certain period of time, it's ending its trip. So there's some terminal point of estimation or calculation, I should say, that is performed on that endpoint for the trip. I just don't know what that is.
Okay, thank you.
Mm-hmm.
Moving over to RJ, a question came in on what is the thought process behind the score ranges?
Yeah, that was an interesting process. So again, what we did is converted the estimated daily volume to capacity ratios and the travel time indices into scores. And sort of the starting point for that was some work that we had done with Florida DOT, but then it really was sort of a combination of sort of an expert panel type input and then assessment of the results. And so we had, as we were conducting this effort, had several meetings with the mobility and safety staff at NCDOT, a bit of trial and error related to those scores and how many sites would pop up on the screening list as a result of those changes, and really just trying to sort of key in on what seemed about right for that network screening list that they could then take, say at the district level and, dig in a little bit further, to determine if that was a good site for a potential spot mobility project. So, some subjectivity there and sensitivity analysis but then certainly some expert assessment of the results by the folks that know that road network well. Again, just sort of in their general judgment on, yep, this is a good starting point of the list that we can, it's manageable and that we can dig in further to determine if those sites continue to have potential for a project.
Okay, thank you, RJ. Another question for Paul. Does the sensor distinguish between cars and trucks?
Okay, thank you. So as I mentioned, when you look at the raw acoustic data that we collect, to some degree, we can see the difference between cars and trucks in terms of the intensity of the acoustic signal that we receive. But actually, we don't use that as our ability to distinguish between cars and trucks at the information layer. It's not something that we can offer now, but we are working on an enhancement to the solution where not only do we count the traffic, but we're also able to categorize the vehicles into the FHWA categories. And we'll do that by detecting the axle spacings of vehicles as they pass over fiber optic road crossings. But I'll stress that that's not available in the solution I described today, but it's something that we are developing.
Thank you, Paul. Back to RJ. A person had a question about what reference you're using to define the thresholds for the volume to capacity index.
I'm not sure I'm completely following, but I think that may be the answer I just gave. Again, we had different thresholds for the converting the actual values to scores, and that was very much an iterative process for that rural spot mobility effort.
Okay, thank you. If the people who ask the questions, by the way, if we don't quite understand the meaning or maybe miss the mark, feel free to rewrite your question and we can re-ask it again. Okay, another question for RJ is, how did you come up with the prioritization list of improvements based from the base list of projects?
So again, our charge was to identify sites for further investigation by the districts, and again, through that sensitivity analysis that converted those V/C ratios and travel time indices to a set of scores, and working with NCDOT staff on just sort of the general, what they wanted for sort of a top tier of sites to further investigate. The way our scoring process worked, that ended up being these sites with negative operational scores, and it resulted in those, I think I mentioned about 610 sites across the NCDOT divisions. There was, quite a nice distribution across those divisions that, again, you could look into those sites further. And so from our client's perspective, that was again, sort of a manageable, reasonable number of a reasonable number of sites that they would look into further. But the dashboard tool provides results for all of the sites, regardless of their operational score, including those top-ranked sites based on the negative scores. From that point, again, there were some comparisons and sort of verification done by NCDOT comparing already been identified to that point with what our results would have provided. And I had noticed recently that NCDOT has started to post online their spot mobility projects that have already been completed or sort of in the queue. And so it'd be sort of interesting to go back and overlay that map with some of our results there with the 2017 data.
Great, thank you. One more question for you, RJ. Can you provide a link to the report? I'm assuming that means if you wrote a report for the project?
We did end up, this was, I think at the time, NCDOT had this need, and it was an, internal effort to help identify these sites. But ultimately, we did write a report. I don't know if it's published, but if anyone would like to drop me an email, hopefully you have my email address from the presentation. I can certainly get a quick okay from NCDOT, hopefully, or clear it with them, and if possible, share the report with you. That provides some more background on the data and methods.
Wonderful, thank you. We've still got a couple more minutes. I don't see any other questions in the question pod. I did have another question for Paul, just to clarify. You mentioned that your technology uses the dark fiber that might be within a collection, a bundle of the fiber optics, and it becomes dedicated for that traffic monitoring use. How does the agency ensure that the dark fiber remains available for your use?
Okay, good question. So generally, in our experience, any whether it's a road authority or any other customer, will keep a record of the fiber optic cables and the cores and the use, what they're being used for. And generally, in any kind of multi-core fiber optic cable, there'll be a relatively high proportion of those which are being unused at any one time. And so generally they will just assign that to us, and then through their own procedures make sure that is kept dedicated to our solution. If for any reason it got disconnected or terminated, then we would almost immediately be able to alert and report on that anyway.
Okay, thanks. Another question did come in for you, Paul. Any other sites in New Zealand reports available for the Auckland site? And this is from David from Wendy, Wellington, New Zealand.
All right. Okay, great. I don't know what time it is for you. It must be in the morning, I guess. Yeah, I have other information which can be provided to you about that project. No problem. I guess Sarah or Kellyanne, you'll be able to make my email available to David, and then he could just contact me, and we'll arrange it like that.
Yes, we can do that. All right. Well, with that, I believe we've come up on our magic hour, and I don't see any other questions in the chat, so I'm going to turn it back over to Kellyanne for closing us out.
Thanks, Sarah. And on behalf of IT, I would really like to